Welcome back students. Today in this class we will see applications of second order differential equations. One of the application is mass spring system. Here we will consider a mass M which is fixed to a spring at end A and the other end is fixed at O vertically as shown in the figure. Suppose E is AB which is the elongation distance due to the mass M and KB the restoring force per unit extension of the spring. Then for equilibrium at P we have mg equal to Ke where g is the acceleration due to gravity. Suppose Pb equal to xb displaced, then the motion starts and the acceleration of the mass m is d square x by dt square. So where x is displacement, dx by dt is velocity, hence d square x by dt square is known as acceleration. The forces acting on the mass are its own weight and mg, and the restoring force is k into e plus x as shown in the figure, which is directed upwards. Then we will have Newton's second law of motion, that is m d square x by dt square is mg minus k into e plus x. So clearly mg equal to ke, so that mg and ke get cancelled, so we will have minus kx. Thus the motion equation is m d square x by dt square is minus kx, or this can be written as d square x by dt square plus k by m into x equal to 0. Now where mu square value is k by m. Now using this we can find the period, the frequency period is given by 2 pi by mu, that is 2 pi into root of m by k. Now the second order differential equation of motion equation can be written in the operator form. The operator form is d square plus mu square of x equal to 0, where d is a differential operator, that is d is d by dx. Now we can write the auxiliary equation. So the auxiliary equation is given by m square plus mu square equal to 0, which is just obtained by replacing capital D with m. And we can compute the roots of the auxiliary equation, that is m square is a negative mu square or m equal to plus or minus mu I. Now the required solution for this second order differential equation, that is a homogeneous differential equation, is given by x is a complementary function, that is cf, that is which is given by c1 mu t plus c2 sin mu t. So x is a cf, that is a c1 cos mu t plus c2 sin mu t, because the roots of the auxiliary equation are imaginary roots. Hence it is the solution which is known as the displacement x. This can be written in the form x equal to a cos mu t plus alpha. So this is the required displacement of the mass m. Suppose if we take cos alpha as c1 by a and sin alpha as negative c2 by a, then the amplitude a is given by a is square root of c1 square plus c2 square, and the phase angle which is given by alpha just by dividing sin alpha and cos alpha, that is sin alpha by cos alpha. Thus we will have tan inverse of negative c2 by c1, which is given by phase angle. Time period or frequency period, the formula is t equal to 2 pi by mu, that is 2 pi into root of m by k. So these are the values for the motion equation. The displacement x is a cos mu t plus alpha, and amplitude formula is a is square root of c1 square plus c2 square, where c1 c2 are arbitrary constants, and phase angle which is given by alpha is tan inverse of negative c2 by c1. The time period is given by t equal to 2 pi by mu, that is 2 pi into root of m by k. Now the forced oscillations of a spring without damping. Suppose to get oscillations, suppose an external force q cos nt is imposed to the system for an instance. The spring is also vibrating. The resulting motion is called as forced oscillations without damping. Now according to Newton's second law of motion, we will have the force is equal to restoring force plus external force. So we will have the restoring force is negative kx and the external force is q cos nt. Just adding these and equating to ma, that is m into d square x by dt square according to Newton's second law. That is force is equal to ma. A is acceleration, that is a is d square x by dt square. So it is the equation of the motion for forced oscillations of a spring without damping. Damped vibrations in a spring, that is a damped vibrations of a spring which is obtained by taking damping force which is directly proportional to the velocity of the mass and acts on the direction opposite to the motion. So here that's damping force value is given by negative c into dx by dt, because the damping force is directly proportional to the velocity of the mass and acts opposite direction, so that we have to take negative. So here c is damping constant and dx by dt is velocity. So damping force is directly proportional to velocity of the mass and acts in the direction opposite to the motion. Thus, the total force is acted. The total force is obtained by using Newton's second law of motion. So we will have the force is equal to the sum of three forces, that is restoring force, external force, and damping force. That is the force is nothing but m d square x by dt square. Here the restoring force is negative kx and the external force is q cos nt and the damping force is negative c into dx by dt. All the three forces are added here on the right hand side, and the left hand side is the force value, that is m into d square x by dt square. Now rearranging the terms, we will have m d square x by dt square plus c dx by dt plus kx equal to q cos nt. So clearly it is the second order dE, it is the required motion equation. So here the motion equation is m into d square x by dt square is negative kx plus q cos nt minus c dx by dt, or m d square x by dt square plus c dx by dt plus kx is q cos nt, where q cos nt is external force, negative c dx by dt is damping force, and the restoring force is negative kx, and k is spring constant, x is displacement. We can calculate the displacement using this motion equation. Problem on mass spring system. A mass m is suspended from one end of the spring, is subjected to a periodic force F equal to F naught sin at in the direction of its length. The force F is measured vertically downwards and time t equal to 0. The mass m is at rest. If the spring constant is k, then we have to prove that the displacement of the mass at any time t is given by x is f naught upon m into p square minus a square sin at minus a upon p sin pt, where p square is k by m. So here the mass m is suspended from one end of the spring and which is subjected to a external force, that is periodic force. So first we have to consider the motion equation. The motion equation from the Newton's second law of motion, we will have force equal to restoring force plus external force. So here only the external force is added to the restoring force. Here external force is nothing but periodic force. According to Newton's second law of motion, we will have the force is m d square x by dt square, where m is the mass and d square x by dt square is the acceleration. The restoring force is negative kx. And the external force imposed to the system is F naught sin at, which is added on right hand side. Thus we will have m d square x by dt square is negative kx plus F naught sin at. Now this can be written as m d square x by dt square, negative kx, if it comes to left hand side it will be positive kx, is equal to F naught sin at. Now dividing the whole equation with m, So we will have d square x by dt square plus k by m into x is equal to f naught sine at. Now it is a second order differential equation. Now to get the required displacement to solve the equation, first we have to take the operator form. For this we have to use the operator d. So here d stands for differential operator, that is d is d by dt. So using differential operator, the operator form is d square plus p square of x is f naught by m into sine at. But where p square is k by m. Now taking the auxiliary equation which is obtained by replacing capital D by m. So thus we will have m square plus p square is 0. That is m square equal to negative p square, or m is plus or minus root of negative p square. That is root of negative p square is pi. So thus we will have m is plus or minus pi. The two roots of the auxiliary equation are imaginary roots, which are in the form alpha plus or minus I beta. Thus, we can write the complementary function as c1 cos pt plus c2 sin pt. That is, CF is c1 cos beta t plus c2 sin beta t whole bracket into e power alpha t. But here alpha value is 0 and beta value is p. So that we have to write the complementary function as c1 cos pt plus c2 sin pt. Now we have to compute the particular integral. The formula is given by 1 by f of dt. That is 1 by d square plus p square f naught by m into sine at. So here f naught by m is constant. Just take it out the constant f naught by m. 1 by d square plus p square sine at. But this is pi second case. In this case, we have to replace d square equal to minus a square. So putting d square equal to minus a square, we will have 1 by minus a square plus p square sine at. While putting d square equal to minus a square, clearly we will have the denominator value is not equal to 0. So that we can put d square as minus a square. Thus, we will get the required particular integral as f naught by m into p square minus a square sine at. So it is the required general solution. Hence the displacement or the position of the mass at any time t is given by x is cf plus pi. So it is the complete solution or the required displacement or the position of the mass at any time t. So which is given by x equal to cf plus pi. That is x is c1 cos pt plus c2 sin pt plus f naught by m into p square minus a square sine at. So let it be some equation number 2. Now, to compute the arbitrary constants values C1 and C2, we have to use the initial conditions. The initial condition is when time t equal to 0, the mass m is at rest. That means there is no displacement. So that is when t equal to 0, we will have x equal to 0. Substituting these values in the equation number 2, we will get the first arbitrary constant, that is C1 value is 0. Since when time is 0, the mass m is at rest, that means there is no velocity, so that the value of dx by dt is 0. Because the displacement while differentiating with respect to time, we will get velocity. The mass m is at rest, so that dx by dt value is 0. Substituting these values in equation 2, for this we have to differentiate the second equation with respect to time, that is t. So differentiating with respect to t, dx by dt is c1 constant cos pt derivative minus p sin pt, and c2 is constant sin pt derivative is p cos pt, and f naught by m into p square minus a square is constant, just take it out, and sin at derivative is a cos at. Now substituting the above values, that is when time t equal to 0, the velocity value dx by dt is 0. Substituting dx by dt equal to 0 and t equal to 0 and solving for C2. Thus we will have the value of C2, that is negative f naught a by mp into p square minus a square. Now substituting the values of C1 and C2 in equation 2, that is the general solution. So hence we will get the required displacement of the mass m at any time t, that is x is f naught by m into p square minus a square sin at minus a by p sin pt. So which is the required displacement of the mass m at any time t, or the position of the mass m at any time t, and satisfying the values, that is the mass m is at rest position at any time t. Thank you.